Okay, so this is our next topic in the discussion around the common things that exist in all programming languages. We've talked about syntax and semantics. The next topic is names. Names are in every programming language, so let's have a discussion about what names are and what they mean, and how the different properties of names are manifested in programming languages. So to talk about names, we talk about what they look like in the language and what they actually mean. In this conversation, we're going to use three terms. We're going to talk about bindings, scope, and lifetime. Bindings is a statement about the various properties that might be associated with a name, what those properties are, what those properties mean, and when those associations are made. We'll also talk about the scope of a name. Where is the name visible? And we'll talk about the lifetime. How long does the name last, and how long do the various bindings associated with names last? So a binding is really just an association between an entity and a property. So if a name is a variable, one property that might be bound to it is its type. One property that might be bound to it is its value. So there's a list of properties, and we'll talk about what those are. When the bindings happen is important. Bindings can either be static or dynamic. Static bindings happen before the program is run. Static bindings are done by the compiler. Dynamic bindings are done at runtime. Now, some things are done statically and some things are done dynamically, and even if you've never heard those terms before, you're familiar with them. So for example, in C++ and Java, the type of a variable is bound to the variable statically. You have to declare the variable at compile time. That's not true in Python, right? When you say x equals 3 in Python, not only are you binding the value to that variable, you're binding the type. The type is bound at runtime, dynamically, not at compile time, statically. Name bindings are very important. They really have a fundamental role in the languages, and sometimes the differences in languages are manifested around when certain kinds of bindings happen in certain languages. So before we dive into the bindings, let's just go through a couple of practical issues. Every language that has names has some kind of a definition for what the lexical rules for names are, and we're familiar with this. It's usually something that begins with a letter, or maybe it's something that begins with a letter or an underscore, and is followed by 0 or more letters or numbers or underscores or whatever other symbols are defined to be allowed in names. Most languages keep a collection of reserved words or keywords. We're familiar with this in our programming projects. We're familiar with this in the programming languages we use. So things like int and if and class are reserved words. They have the same syntax as names in the language, but they're reserved. They can't be used as names because they're already reserved to be keywords in the language. Some languages don't care about case sensitivity, other languages do. C-like languages like Java and C++, names are case sensitive, so the variable hello with a small h and the variable hello with a capital H, those are two different variables because the languages are case sensitive. This isn't always true. SQL isn't case sensitive. Languages like HTML aren't case sensitive. You can spell title with all lowercase letters or all uppercase letters. It doesn't matter. This is really just a design decision made by the designers of the programming language, and somewhere in the syntactic description of the language it says things like names are case sensitive or names aren't. One brief thing to talk about reserved words. Reserved words usually reserved words can't be used as identifiers. They usually identify the major keywords in the language. In some languages, other predefined things become reserved words. In some languages, library routines might be reserved words, but in others, like the ones you're familiar with, library routines are just names and they're not reserved words at all. Okay, so now let's get into the details of what bindings are, what it means, and what we might actually care about here. There are 5 basic bindings associated with variables: name, address, type, value, and lifetime. Variables have these bindings associated with them. A name is bound to a variable, and it's just, following the lexical rules of the language. Address is a binding that indicates where in memory a particular variable lives, and how that's decided, and where that actual memory is. It depends on the language. Type is another binding associated with a variable, and type is a big enough topic that we're going to save it for another lecture. So we, other than the fact that informing you that type is a binding, we're not going to spend any time on the details of type because that's the next topic. And the other binding that can be associated with a variable is a value. What's stored in the memory that's bound to the name. So if I say int x equals 3, the name for that variable is x, the type for that variable is int, the address is, well, somewhere, we'll get to that in a moment, the value that's bound to it is 3. When you assign a value to a variable that you've declared, you're simply changing the value that's bound to that variable. The old binding goes away and the new binding takes effect. So if x used to be 4, and then I say x equals 6, the old binding of the value 4 to x is discarded, and the new binding of the value 6 to x is established. Then there's lifetime of variables, which depends on the kind of variable and depends on the language, and we'll talk about that as well. Now, in order to know what addresses are bound to variables, let's remind you of a couple of things about memory. As we discussed before, memory is divided into several regions in the operating system. Depending on your runtime environment, the operating system may have certain permissions associated with those memory regions or not. That's up to the runtime. The runtime manages memory and sets things up. There are 4 regions: code, data, heap, and stack. And those are the addresses in those 4 regions are the possible bindings. Now, the actual bindings that are used, the actual memory that's used in all these languages, depends upon the position of the variable declaration in the language. Because of where a variable appears statically in the program, the compiler is able to determine statically which memory region is bound to the variable, and which particular address is bound to the variable is just sort of done in sequence, right? The first global variable is assigned memory in the data segment, and then the next global variable is assigned memory right after that, etc., etc. Right? This code fragment here on this slide tries to illustrate all these things. I've named this variable outside to show you that it's outside of function declaration. It's an external variable or a global variable. It is bound to some address in the data segment, and the compiler and the linker will work together to figure out which particular address that is, but that address is statically bound at compile time. right underneath that variable declaration is a declaration for a function called myFunction. The code for that function goes into code segments somewhere. And you can see that there are two variables declared inside that function. A variable named x, which is of type sum class, and a variable named p, which is of type pointer to sum class. Because those two variables are declared inside the function, the compiler will cause them to have a memory address that's somewhere on the stack bound to them. So the memory address for x and the memory address for p will be a memory address somewhere on the stack, and that binding is handled partly at compile time and partly at runtime. And we will talk about the details of that when we talk about functions. You can be guaranteed that those variables will be on the stack somewhere. Where exactly on the stack? It depends. Depends on the calling sequence of the order in which the functions are called, and what's called when, and we'll talk about that in detail when we examine functions. The last line of code here, you can see I've invoked the new operator. I've said new sum class. That causes me to get some memory from the heap. So dynamically, at runtime, I get memory from the heap, and I bind that memory address to p. It's a little bit more complicated than that because p is a pointer, so it's actually the value that is bound to p is an address. So p is on the stack, but the address that's stored in it, the value that is bound to it, is on the heap. A couple other pieces of terminology for you to be aware of. I've mentioned these in previous lectures, but it's good to reiterate them. When we are trying to assign to a variable, when a variable appears on the left-hand side of the equal sign, what we're trying to do is change the value that is bound to that variable. We change the value that is bound to that variable by storing some value in the memory address that's associated with that variable. So the memory address that is bound to x contains the value that is bound to x. And when we care about assigning to a variable, we say that we care about the variable's L value, the value that you use when it's on the left-hand side of the equal sign. The L value for a variable is the address that is bound to that variable. And we store things in that address to bind a value to a variable. On the bottom, we see the use of x in an expression, right? So it's somewhere on the right-hand side of the equal sign there. So we use the phrase R value. The R value of a variable is the value that is bound to the variable. So the L value is the address that's bound to the variable, and the R value is the value that's bound to the variable. Assigning to a variable binds the value to the variable by storing something in the L value. Using the value that's been bound to a variable, we're using the variable's R value. So I've tried to lay all this out in this slide here. So you see here, I've just got a bunch of variables declared. X, Y, and Z. In the case of X, Y, and Z, the R value for X is whatever integer is stored in X. The R value for Y is whatever integer is stored in Y, etc. The L value for X, the L value for Y, the L value for Z is the memory address associated with X, Y, and Z. Maybe it's on the data segment, maybe it's on the stack, maybe it's in the heap, nobody cares, nobody knows. It's different from the R value. A pointer is a little different. It's useful to think about pointers by recognizing that pointers actually have, I guess you could say, two different natures, right? A pointer is a variable. So the pointer has an L value. That is to say that there's an address somewhere where that pointer is stored. The R value that's associated with the pointer is the value that's stored in there, the numerical memory address that is being saved in the variable is the R value. The R value of a pointer is somebody else's L value. Okay, so when I say P equals an address, if I say P equals address of X, I'm storing X's L value in P. So because pointers have this idea of a dual nature, that they are both a memory address and you might also care about what the memory address points to, we use this star operator. Okay, so star is the pointer dereference operator. If I say star P and I use it as an L value, that means that I am caring about what the pointer points to and I want to store something there. If I have star P and I'm using it as an R value, that means I care about what's stored at that pointer's location. So if you see at the bottom there where I said P equals address of X, Y equals star P equals Z, P equals address of X makes P point at X. So P's R value is X's L value. In the next line I say Y equals star P. Star P says go to that pointer, get its memory address, go to that pointer, get the value that's associated with that, which is a memory address, and then follow it. Okay, so star P says, what does P point to? Well, P points to X in this case. So star P is associated with X. Star P on the right-hand side of the equal sign is whatever value is stored in X, copy that into Y. The last line, star P equals Z. Star P equals X, or star P points to X, so star P refers to X. Star P on the left-hand side of the equal sign is the same thing as X on the left-hand side of the equal sign. Star P on the right-hand side of the equal sign is the same thing as X on the right-hand side of the equal sign. So if I assign to P, I'm changing the pointer. If I assign to star P, I'm changing what the pointer points to. If I use P, I'm using the pointer. If I use star P, I'm using what the pointer points to. The next useful topic here that it's important to understand about names is the scope of names. Scope is about visibility. Scope is another way of saying what lines of code can see a particular name. Okay. There's two kinds of scoping, static scoping and dynamic scoping, and just about every language that we can think of here is using static scoping. Static scoping means that you can tell the scope of a variable by looking to see where the variable appears in the program. Okay, so the scope of a variable in a statically scoped language like C and C++ and Java, the scope of a variable can be determined just by looking at it, just by seeing where it is in the program. Okay. And scopes are either nested or disjoint. That is to say, one scope is either completely separate from another, or one scope is completely enclosed one inside of the other. Okay. And there's a lot of different things that can be scopes, right? There's a global scope, and everything in the global scope is visible to everything else. And then there's file scope. File is a compilation unit, a source file. And then there's other scopes which are certain subdivisions of the code. So if you think about it, if I've got two files, each file is its own scope. So those two scopes are completely disjoint. It's either one file or the other. Everything ends up being in the global scope. Everything is nested in a global scope. If I write a program and I've got 3 functions, right? Each one of those functions is in the global scope. There are also various subdivisions. If you're a Java programmer, you're used to packages. Packages are a scope. Namespaces are a scope. And these things can be nested. You can have a package inside of a package. You can have a namespace inside of a namespace. You can have classes inside of a class, right? Classes are a scope. Functions are their own scope. Blocks of code, curly brace enclosed clumps of code are their own scope. And in C++ and Java, even for loops are their own scope. Okay, and none of these things overlap. A block is either completely separate from another block or completely enclosed inside of another block. A for loop is either completely separate from another for loop, or the for loop is completely fully nested inside of another loop. There's no way of writing, think of a Venn diagram, right? There's no way of having one block and another block and have only part of them overlap. That's what we mean when we say that the scopes are either disjoint or nested. Okay, so the reason we care about this is that the scope in which a name is declared determines its visibility. Okay? The scope in which a name is defined or declared is called the defining scope. And a reference to a name is non-local if it's in a nested scope, otherwise it's local. So let's give you an example here. This is a short little program, 10 lines of code. And there's a whole bunch of things going on here, right? There's a function, and there's a for loop that begins at line 3, and there's a for loop that begins at line 4, and there's a for loop that an if statement that begins at line 5. Now, let's just take a look at this. Let's look at it from the inside out. Lines 6, 7, 8, and 9 are in a block. That block is its own scope. The if statement that begins at line 5 is inside of the for loop that begins at line 4, which is its own scope. The for loop at line 4 is inside of the for loop at line 3. So there's a scope that begins at line 3, and completely enclosed inside of that is a scope that begins at line 4, and completely enclosed inside that is that block that's 6, 7, 8, and 9. And all of that, all of those nested scopes are inside of this function, this sort function, and the function is in whatever file it's in and is part of the global scope. So there's lots and lots of things going on here. If you look at line 3 and look at the comment there, you'll see, so that's a for loop, I from 0 to size. And I is declared in that scope. Saying int I equals 0 declares an integer there named I. That I is declared inside of that for loop scope. Therefore, all references to I there are local. Size is not in that for loop scope. It's in the enclosing scope. It's in the function scope. It's one of the arguments. Next line down, line 4, now I'm in another scope, nested inside of the for loop at line 3, which is nested inside of the function. The scope at line 4, you can see, declares a variable named j. That j is local to this scope. I is not local. Size is not local. Similarly, on line 5, j is local, I is not local, A is not local, and then all the way down in 7, 8, and 9, line 7 uses the variable t, which is declared at line 6. That's local. A and I are not local. On line 8, all of those variables there, A, I, and J, are all non-local. So there has to be some kind of a process to figure out if something is local or not local. And if something's not local, you gotta find it. Okay? And you either find it or you don't. If you find it, great. And if you don't find it, then the variable's not declared. It's an unknown symbol. That's where that compiler error comes from. A simple example of this can illustrate this point. If you take a look at this program here, this little code snippet here, I got a for loop. So you see that for loop is its own scope, right? It's entirely contained in that for loop. And I've declared a variable named I. I initialize it to 0. I go all the way up to 10. So this, that little snippet of code prints out 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Great. Now the line after that says, if I is equal to 10. What is I? Well, I isn't local, and it's not remote either. It's not non-local. The scope of I is just that for loop. So the I in the if there, if I is equal to 10, the compiler doesn't know what that I is. It's an I in some other scope that it doesn't see. So the I is out of scope. We'll see some more examples of this in just a moment. Now, programming languages give you, the programmer, some control over the scope of things. Right? The keyword static has stuff to do with memory binding, but it also has stuff to do with scope. A function that is declared to be static, or a variable that is declared to be static. If they're external, that function, that variable, are private to the file. I think I mentioned this sort of thing in the last lecture. You can control the scope of certain members of classes in C++ and Java and other languages that support object-oriented programming. Saying that something is private, saying that something is public, saying that something is protected is really just a statement about scope. If something is private, I'm restricting the scope of that variable so that it's only visible inside of the class. If something is public, I'm saying that the scope of that variable is anybody who wants to look at it can. And if the scope is protected, I'm saying, if the specifier is protected, I'm saying that the scope of that variable is this class or any class that inherits from this class. So it's the notion of what is private and public and protected is really just a statement about scope. In Java, you can use the dot operator as a scope resolution operator. So you can say, package name dot subpackage name dot subpackage name dot class. C++ doesn't do that. Instead, they use the scope resolution operator : : So when we say standard ::cout or standard : :cin. What we're saying is we're using the scope resolution operator. Go to the standard namespace and then look in the standard namespace for cin or cout. Okay. Now let's talk about how this stuff ends up getting used practically. Sorry about that. Data structure can be any implementation that you want. It's generally some kind of dictionary where the name is a key and the value is all the bindings. Okay, and the process of either compiling or interpreting and figuring out what's what is using the symbol table, building the symbol table, and searching the symbol table. So you basically keep a stack of symbol tables. Each time you enter a new scope, you push a new dictionary onto the stack. Each time you exit the scope, you pop the dictionary off the stack. Each time you declare a name, you generate the binding and you enter the name binding into the dictionary. Right? And it's at that point where you say, you're trying to declare a variable named I, but you already have a variable named I in this scope, so you're not allowed to do that. Okay. Then the important trick here is, okay, now how do I resolve names? So every time a name appears, I search the dictionary on the top of the stack. The dictionary on the top of the stack represents all the local bindings, all the locally defined variables. So if I use a symbol, and the symbol happens to be a local symbol, I will find it and return the binding. Otherwise, I keep snaking my way down the stack. If it's not in this scope, I look in the next dictionary on the stack, and the next dictionary on the stack, the next symbol table, is the symbol table for the stack, the scope that I'm enclosed in. And then if I don't find it there, I look in the next one, the symbol table that scope's enclosed in. So if scopes are nested to depth 5, the stack of symbol tables is 5 deep. You search local, then you search the next one, then you search the next one, until you find it. And if you don't find it, that's an error. Okay, so this code fragment here, okay, which we looked at before, right? There's going to be a symbol table associated with the scope at lines 6, 7, 8, and 9. Underneath that there's going to be a symbol table for the scope at line 4. Then there's going to be a symbol table for the scope at line 3. Then there's going to be a symbol table for the scope at line 1, right? That there's a function and its arguments. And then there's going to actually be a global scope as well. So there's going to be a whole nesting of stacks. At any given line in the code, the top stack, the top scope on the stack is the local scope, and you just keep looking. So you see here, in the rightmost column here, we say at line 7, the top of the stack is the scope in which T is defined. At line 5, the lower left-hand side of the slide, you'll see that we haven't entered that scope yet, so there is no symbol table on the stack for T. At line 7 or line 8 or line 9, it's perfectly okay to access the symbol T because we'll find it. At line 5, if we tried to use the symbol T, we wouldn't find it. It's not there. When we talk about static scoping, we talk about the referencing environment. The referencing environment for a name, that is to say, the place where a name is visible, is the scope in which it's defined and all the nested scopes underneath it. So, The only people who can see and reference a name are the people in that referencing environment. If you are either in the scope in which the name is defined, or you are in a scope that is fully nested inside of that scope where the name is defined, then you can see the name. Otherwise, you just can't. So an example here should help illustrate this. I have a simple little program here. You'll see I have two variables named h and I declared on line 1. I have a function declared on line 2. I have a function declared on line 8. I have a function declared on line 14. So there's a global scope at which the names h, I, b, a, and main are known. The function b is its own scope, so the code in lines 3, 4, 5, and 6 there, that's the body of b, that's its own scope. The scope associated with the code at lines 9, 10, 11, 12 is the scope for the function a. And as you can see, b and a are completely disjoint, and main is also completely disjoint. So notice in main, I say int ab, I assign to h, I assign to a, I assign to b. Well, wait a minute, look at line 16. I'm assigning to h. Where is h? I don't know what h is. Let me search this scope. Well, the scope's the scope for this function. It's got a and b in it, and geez, I don't see h anywhere. I better check the enclosing scope. I better check the scope that I belong in, or that I'm defined in, and when I do that, I find the h that's at line 1. Okay, so the code at line 16 assigns 5 to the integer h that's declared at line 1. Yay, and away we go. Line 19 makes a call to a, and line 20 makes a call to b. So let's look at the code in the function a. Right? A's got a variable named I and j. Okay, and it makes a call to b. So again, it's making a call to b, it's passing it the argument h. I don't know what h is. H is not defined in this scope. Let me search the scope in which my scope is enclosed. Oh, I'm going to find h at line 1. Great. There we go. So the code at line 10 passes h to the function b, and the h that it passes is the integer at line 1. Now we take a look at line 11. Line 11, we assign I the value 3. Okay, what's I? Well, okay, I is that variable that's declared there in on line 9, so I'm going to assign a 3 to that floating point variable. But wait a minute, you're saying, I've got an I declared at line 1. There's an I declared at line 1 and an I declared at line 9. Yes, that's correct. The I that's declared at line 9 is the locally defined I, and when I search for a variable named I in this function, that's the I I'm going to find. I'm going to search first the local scope. Oh, there I found an I. So that's the I mean. The I that's assigned to at line 11 is the I that is declared at line 9. The H that is declared, used at line 10 is the H that's declared at line 1. Now you might say to yourself, gee, that sounds like it means that the I at line 9 hides the definition of the I at line 1. And in fact, that's exactly what it means. A declaration in a local scope is found before any declaration in any enclosing scope. So that's what's found. The outer declarations are actually hidden. Inside the function b, you'll see that we refer to, at line 4, we refer to the variable I. This time there's no I declared in the local scope to hide anything. So the I at line 4, that's used at line 4, is the I that's declared at line 1. So the I that's declared at line 1 is the I that's used at line 4. At line 4, we search for I, we find the I at line 1. At line 11, we search for I. The I that we find is the variable that's declared at line 9. And the one that's declared at line 1 is hidden. For all we know, it doesn't even exist. We don't see it. So these slides here just show at various times and in various places the variables that are declared and where they're declared, and you can see the stacks. So you can see here how in the function a, the I that's declared at line 9 hides the I that's declared at line 1. Now there's one other topic that I want to mention here. You won't necessarily come across this very often, right? Earlier on I said that C and C++ and Java, and indeed most of the languages we use these days, use something called static scoping or lexical scoping. But there is a thing called dynamic scoping. In dynamic scoping, a name is bound to its most recent declaration based on the program's call history. Now this is used in some early programming languages. It's used in APL. The symbol table is built at compile time, but it's managed at runtime. So in a way, you don't care how the code's written, but you care how it executes. A lot of programming languages, modern programming languages, have sort of abandoned dynamic scoping because it's terribly confusing, right? Static scoping or lexical scoping is easy. I look at the variable, I look at where it is in the program. Just by virtue of where it is in the program, I know what its scope is. But in dynamic scoping, it depends the order in which the program's executed. So here's an example of this, right? On the left-hand side, I wrote a C program that has static scoping, right? So main calls G calls F. G has an integer named x, and that x is declared inside of the scope of the function G. It's only visible inside of G. G calls F. F returns x. Well, there is no x declared in the scope of F, so it's going to find the x equals 10 global at the top of the program. So running this program prints 10. The program on the right illustrates dynamic scoping. Okay, so here, the order in which things are executed matters, right? So in main, you'll see that first x is declared to be 10 up at the top. Then in main, I call G. G declares an x named 20, an x with a value of 20. Then it calls F. F returns x. In dynamic scoping, it's the x that was most recently declared, not any static x based on the appearance of the variable in the program. So as a result, the statically scoped version of the program prints 10. The dynamically scoped version of the program prints 20. If the dynamically scoped version of the program called F instead of G, it would print 10, because the call to G is what generates the x equals 20. And if you're saying to yourself, wow, that's really confusing, you're right. It is really confusing. It's very difficult to debug something when the actual variable depends upon the order in which the program is running. It's hard enough to debug things when the value associated with the variable depends upon the running sequence of the program. So you don't see this very much at all. But I call it to your attention in case you read about it, or you come across an old programming language like Lisp that uses it. Okay, the next thing I want to talk about is visibility. Okay, the visibility of a variable talks about how you can get at variables, what variables you can see. Name's visible if it's in the referencing environment and it's not redeclared. Okay, so this is just another way of talking about the thing I mentioned earlier. If a name is visible if it's not hidden. If I declare a variable and I don't redeclare another variable with that name inside an enclosing scope, then everybody can see that variable. Otherwise, it's hidden. So the definitions of names in inner scopes hide the definitions in the outer scopes. And most of the time this is okay. Sometimes we don't necessarily like this, and some languages give you a mechanism to sort of get around this restriction. Right? The variable, the keyword this, you can think of as being a way to get around hidden names by explicitly saying where a particular variable is. So take a look at this example here. This is a class definition, which we set as a scope. And declared inside this scope, you can see I've got a variable called name, which is a string. Then I have a method, which is a constructor from lines 3 to 6. That method is a function. It's a scope. Right? And that scope is completely enclosed inside of the scope for the class. So you'll notice that I have an argument to that constructor, which is called name, and that argument, which is called name on line 3, is going to hide the member, which is declared at line 2. So that's sort of no bueno, right? I mean, inside that method, now I've hidden the variable declared at line 2, and I can't access it. But this is a constructor. I need to initialize it. So the keyword this comes to the rescue here, right? Line 4, I say this.name. The variable called name that's associated with this particular instance of the class, should be set equal to the variable called name, which is the parameter passed into the function. So saying this.name gives me access to the variable at line 2 that would otherwise be hidden. An analog to this is this piece of C++ code. I declare a variable called count at line 1, and then inside of a function at line 3, I declare another variable called count. The scope for the function declared between lines 2 and 6 is completely enclosed inside of this file scope. The declaration of count at line 3 hides the declaration of count at line 1. So if I try and assign to count on line 4, I'm accessing the count that I declared at the local scope. The externally declared count is hidden. But I can use the scope resolution operator to get around that, right? So : count says, go up to the global scope and get the count variable that should find there. So similarly to saying this.name, so that I can get it a name that would otherwise be hidden, : count gets it count, which would otherwise be hidden. There's another sort of variation here that is important to understand and worth discussing, and that's the concept of overloading. Okay? Overloading uses the number and or the type of parameters to distinguish among identical functions. Okay. So there's really a bunch of different kinds of overloading, and some of them we've already talked about sort of ad nauseum in class, right? Plus, minus, star, and slash are the operators built into the language that handle addition, subtraction, multiplication, and division. They add integers together, they add floating point numbers together, and if you, say 2 plus 2, the compiler is smart enough to know that because of the types that you are using with that operator, it knows to do integer addition. Similarly, plus can be string concatenation, right? So string plus string, the compiler sees that the operands are of type string, so it knows to do string concatenation. Another version of overloading is, or an example of another version of overloading, is the system out print function in Java. This is an example of this sort of general idea of allowing you to overload function names. So here you'll see that there's a bunch of different functions named print. And you might stop and say, wait a minute, I thought you said that you can't have duplicated names. And yet here you have the name print repeated 1, 2, 3, 4, 5, 6. You have this name print repeated 9 times in this scope. Haven't you created a problem with duplicating the name? Well, no. For the languages that support this, they say that the name of a function is the name of the function and the type of its arguments. So the print function that takes a Boolean is different from the print function that takes a float. It's different from the print function that takes a string. And so what you end up doing is you call print. And the compiler figures out which print you mean from the type of the argument that you pass it. Okay? So just like when you say 2 plus 2, the compiler says, okay, that's 2 integers, so I'm going to do integer addition. If you say system out print hello world, the compiler is going to say, I'm going to use the version of print that takes a string because hello world's a string. And in fact, C++ operator overloading works just like that. Operator overloading is simply the declaration of a function, and that function takes, if the operator has 2 operands, the function has 2 arguments. So if I say my class plus my class, then the compiler needs to find a version of operator plus that'll work on 2 my classes. And if it does, it just calls that function. It calls that overloaded function. One shame about function overloading in general is that while you can overload functions by changing the types of arguments or the number of arguments, you can't change the return type. In this example, print always has to return a void. Very annoying. Okay. So just a couple more things to talk about with names. The last thing really is to talk about the lifetime of names. Okay. The lifetime of a name is when the name actually exists. Okay. Um, and this is a pretty straightforward concept, right? If you have a global variable, if you have an external variable, like count in our earlier example, that variable is statically declared and statically allocated. There's only one count in that example, and that variable, the location of that variable is known by the compiler. The address binding for that variable exists for the entire lifetime of the program, and so the lifetime of the variable is the entire run of the program. Interestingly, if you have a global variable which is a class, and the class has a constructor, then unbeknownst to you, the C++ compiler is generating code to call that constructor before you call main, because that variable is supposed to have a lifetime of the entire run of the program, and part of the definition of classes is for their lifetime, the first thing that's done with them is they're constructed. So a global class definition, like in the second programming assignment when I had that global map between token types and strings, the compiler was actually doing the constructor for that map and the constructor for all the elements of that map at the very beginning of the program before main was even called. And then after main returned, the very end of my program, after main returned and before my program stopped running, destructors for that variable were called. Now that's great for static allocation, and in early programs or early programming languages, everything was statically allocated, but Algol and all the languages that we're used to using now use dynamic allocation, that memory is dynamically allocated and deallocated when you enter a scope and leave a scope. So when you call a function, the variables needed by that function, the variables declared inside that function, have memory addresses assigned to them immediately when the function is called. And so those variables exist. Their lifetime begins. When you return from the function, that binding goes away. Any memory that was bound to those variables goes away. Those variables don't exist anymore. So variables in a function only exist during the lifetime of the function call. They are created when the function is called. Memory is bound to them. They can be used. And then when you return, that memory is given back and that stuff is destroyed. So when we talk about functions, we'll see how every time you call a function, there's this complicated process going on under the hood of making sure that there's enough memory for all those variables. Also, earlier we talked about nested scopes, right? So, a for loop has a variable, and a nested for loop inside of that might have a variable. That means that every time you enter a new block, every time you go into a new scope, there might have to be memory allocated. The lifetime of the variable inside of that nested scope begins. And then when you leave that scope, the lifetime of that variable ends. So the last thing I want to talk about is static variables and the use of the static keyword and what it means when you're associated by names. Okay, so when you declare something externally, you're basically putting something at global scope. When you declare a variable outside of a function, or frankly, when you declare a function, those things exist at the global scope, and they exist forever. If you have a global variable and you declare it static, then that means that the variable still exists forever, but you've changed its visibility. It's only visible when it's in scope. That is to say, if it's a global variable, it's only visible in the file that it's declared. If you declare a static variable inside of a function, it exists forever. It's in the data space. It exists forever. Its lifetime is the lifetime of the run of the program, but it's only visible inside of the function in which it's declared. So you can sort of think of a static variable inside of a function as a variable that is private just to that function. And you can think of a global variable that you've declared static as a variable that is private just to that file. Now why would you want to do that? Or why might you want to do that? Well, you might have some data structure that's shared among 3 functions but is otherwise private to them. You might want to have a static variable inside of a function so that the first time a function is called, maybe you do some complicated calculation and you cache the result of that calculation in the static variable. And then the second time you call that function, you just look for the cached value instead of redoing the calculation. Any of a number of these things is possible and reasonable. You can also have static class members and static methods. Static class members means that there's only one instance of that particular variable for the entire class. So if I have a class and I create 1,000 instances of the class, each one of those instances has its own copy of instance variables, but they all share the same static variable that you declared. Similarly, you can have static methods in C++. A static method is not called by using a particular instance of an object. In fact, static methods don't need an instance of an object, can't use an instance of an object, and have no real mechanism at all to access individual instance variables. A static method can only access a static member. And static variables and static methods in C++ inside of classes work exactly the same as static members and static methods inside of Java classes. The static variables are shared amongst all instances. Static methods can be called without actually having to create a class. The static methods can't get at instance variables, but they can get at static variables. And that is it for names. Hopefully you've made it through all this, and you should, when you are done watching this, keep track of your questions, and we'll go over those questions either by email if you want to email them to me, or in class next time we meet. So, thanks. Talk to you soon.